Hello friends, welcome to lecture series on essential mathematics for machine learning. Now in this lecture we will see some of the important aspects of support vector machines. Now let us start. So first of all, what do you mean by machine learning? So the term machine learning basically deals with learning from the data which could be in the form of images, measurements, observations, patterns or records. So suppose you have some data which may be in the any of the form of maybe in the form of images, measurements, observation, patterns or records, then learning from these data is basically called machine learning. Now what is the aim of any machine learning? The aim of any machine learning algorithm is to perform well on the training data and also to ensure good results in future. Whatever training data we choose, in that training data, machine learning algorithm should perform good and it also give good result, also ensure good results in future. Machine learning involves the study of three main problems. What are three main problems? Classification, next is clustering and next is regression. So these are the three important problems of any machine learning algorithms. There are many approaches available in the literature to deal with these problems. These problems means classification, clustering and regression. To deal with these type of basic problems of machine learning, there are many algorithms given in the literature. Now Mangasarian has introduced an approach called mathematical programming approach. So there is one approach which is called mathematical programming approach and that was given by Mangasarian. What is the advantage of this approach? Why we are using this approach? Why not some other approach? So the advantage of using this method is that most of the problems involved in machine learning result into linear programming problems, very simple to handle, quadratic programming problems or some convex programming problems. And we already know that if we are having some convex optimization models or convex programming problems, then the KKT conditions become sufficient. Sufficient means that whatever KKT conditions we are having, the point which satisfy those KKT conditions will be global minimum point of the problem. So this is the main beauty of using mathematical programming approach, that it results into either linear programming problem or quadratic programming problem which is very easy to handle. Now machine learning techniques are broadly classified into two classes. Number one, supervised learning and number two, unsupervised learning. The problem of classification and regression comes under supervised learning, while the clustering belongs to the class of unsupervised learning. So we are not going much detail of this topic. We are focusing on this lecture on support vector machine. So this is simply introduction of machine learning. Now what is support vector machine? Wapnick has developed this theory. So they has developed the support vector machine algorithms. The main advantage of SVM over other methods is that it results a convex programming problem and hence we always obtain a global optimal solution because it is a convex optimization model. Moreover, the KKT conditions become sufficient. So this is again the same advantage of as we are having for mathematical programming approach, the same advantage here for using SVM. Let us discuss binary pattern classification problem we are discussing here, just to introduce you what SVM is. So first of all, what do you mean by binary class? Binary class means two class. Okay. Now if you are having two class and you want to classify these two classes, then what are different methods? How we can classify the two classes? Now these two data sets are not very small, these are big class of data sets. Okay. And what are different algorithms by which this big class of data set can be separated, can be classified? Now first of all, here if we are saying pattern, so pattern means an element of Rn. We already know what Rn is. Rn means is set of n tuples. So, pattern means an element of Rn. Let M1 patterns having class of label +1 and M2 pattern having class of label -1. You are having two classes. One class I am denoting by +1 and the other class I am denoting by -1. So, suppose the data points of +1 class are M1 and the data class of -1 points, I mean -1 labeling are M2. So, total how many points? Total there will be M1 plus M2 points. Okay. So, we are denoting, if we denote it by a matrix of this class +1 class, okay, having M1 patterns, and each pattern is in Rn. So, it will be a matrix of order M1 cross n, that means a collection of M1 patterns having class of label +1. And similarly, if we say -1 labeling, so class of -1 labeling will be denoted by this matrix, which is order M2 cross n, that is a collection of M2 patterns having class of label -1. So, this is the first thing, that you are having two data sets, one I am denoting by +1, other I am denoting by -1. My aim is to classify them. Okay. Now, they are these two classes A plus and A minus. Okay. These are said to be linearly separable if there exists a hyperplane W transpose x equal to B, where W is in Rn and B is in R, such that for A plus this is greater than EB and for A minus is less than EB and E is a vector of ones. See here this blue squares, this denote data points of +1 label, that means A plus class, and this circles, this denote another class which is of -1 label and denoting by A minus. So, since you are able to find a hyperplane which is W transpose x equal to B, such that these two classes are classified, so we say that these two classes are linearly separable, and if it is not possible to classify them linearly, then we say that they are non-linearly separable. Okay. So, let us discuss this by an example, so that it will be clear to you that when two classes are said to be linearly separable. Suppose you are having patterns like A plus patterns are suppose 1 1, 1 2, 2 1, 3 2 and 4 1. These patterns are in R2, of course, patterns are in R2. That means here n equal to 2. Okay. So, now how many patterns in A plus class? 1, 2, 3, 4, 5. So, there will be 5 patterns in A plus class. So, A plus will be a matrix of order 5 cross 2, and what is this matrix will be? This will be 1 1, 1 2, 2 1, 3 2 and 4 1. This is 5 cross 2. Okay. Now, if you take another class A minus, suppose is of order say 4 cross 2, which is given by 6 2, 2 6, 7 1 and 7 3. It is 4 cross 2. So, here I am considering two classes, this by label +1, this by label -1. This of these there are 5 patterns belonging to A plus class or +1 class, and there are 4 patterns belonging to -1 class. Now, if you try to plot these points 1 1, so suppose it is 1 1, 1 2, so it is 1 2, 2 1, so it is 2 1, 3 2, so it is 3 2, 3 2, then 4 1, so it is 4 1. Okay. So, these are plus 1 label, okay, A plus. Now, what are A minus? 6 2, 1 2 3 4 5 6. So, 6 2, 6 2 means this point, 2 6, 2 6 means somewhere here, suppose 2 6, okay. 7 1, 7 7 1 means somewhere here, 7 3, 7 3 means somewhere here. So, these are of my A minus class. Okay. Now, clearly you can easily visualize that you can find a hyperplane here may not be unique, okay, but you can find a hyperplane such that these two classes are separable. So, since we are able to find such hyperplane, so we say that these two classes are linearly separable. So, suppose I am predicting one hyperplane. So, one hyperplane you can say x plus y equal to 6, it is x, it is y, it is 6, it is 6. Okay. Now, so if you take, it is x plus y equal to 6, if you take a plus times 1 1, okay, this is W1 is 1, W2 is 1, okay, this is 1 1. So, it is now less than equal to, if you take 6 times 1 1 1, it is 1 2 3 4 5, 1 2 3 4 5. So, this you can easily verify. See, A plus is what? A plus is this matrix. So, this row, this column, the first row, first column is 2, 2 is less than 6, true. Now, this row, this column is 3, 3 less than equal to 6, true. Again 2 plus 1 3, 3 less than equal to 6, true. 3 plus 2 5, 5 less than equal to 6, true. 4 plus 1 5, 5 less than equal to 6, true. So, here this is your W, this is your W, this is your W, and this is your E, vector of ones, this is your E, this is B, B is here, this is B. So, this is satisfied. Now, again if you take A minus 1 1, so it is greater than or equal to 6 times 1 2 3 4, so it is 1 1 1 1. Here is this vector, I mean it is 4 cross 1, here is 4 cross 5 cross 1. Okay. Now, if you take A minus 1 1, 6 plus 2, because first row first column is a matrix multiplication, first row first column is 8, 8 greater than or equal to 6, true. It is 2 plus 6 8, 8 greater than or equal to 6, true. 7 plus 1 8, 8 greater than or equal to 6, again true, and 7 plus 3 is 10, 10 greater than or equal to 6 is again true. So, this is true and this is true. So, we can say that this hyperplane, you can opt for this hyperplane which classify these two classes linearly. Okay. So, hence we are having this definition A plus W greater than EB and A minus W less than EB, okay, where E is a vector of ones of appropriate dimension, it depends what A plus or A minus is. So, if it is not linearly separable, so we are having some non-linear curve here. So, we say that they are non-linearly separable. Now, the question arises, geometrically if we are having a very small data points of A plus class and A minus class, we can geometrically visualize that whether they are linearly separable or not, but in practical applications it may not be true. In practical applications we have a large data sets. Now, to see whether these two classes are linearly separable, the given classes are linearly separable or not. So, what are different methods? Okay. Because once they are separable, then only we can predict the properties of the classes. So, the first property is given by Mangasarian. This property is given by Mangasarian. What is the property? Property is, let A and B be two finite sets in Rn. Then A and B are linearly separable if and only if their convex hulls are disjoint. So, this is the first property that by which we can say that whether two classes are linearly separable or not. So, what do you mean by convex hull? Convex hull is a smallest convex set containing that set. Suppose you are having 3 points. So, what is the smallest convex set containing these 3 points and the set is convex? The smallest convex set will be this set. This set is the smallest convex set containing these 3 points and the set is convex. So, this is the convex hull of these 3 points. Okay. So, let us understand this by an example. Let us suppose A plus has 3 points. The 3 points of A plus are minus 1 0, 0 1 1 0. So, A plus, the points of A plus are minus 1 0, 1 0 and 0 1, and the points of A minus are 0 0, 1 1, 0 2. It is 0 0, 1 1 and 0 2. Let us see. Okay. Now, what are points of A plus? Minus 1 0, minus 1 0 is somewhat here, 1 0, 1 0 is somewhere here, 0 1, 0 1 is somewhere here, something here. Now, what is the convex hull of these 3 points? The convex hull of these 3 points is this triangle. Okay. This triangle. Now, let us see what A minus is. A minus is 0 0. So, this point I am denoting the points of A minus by cross sign. Okay. And 1 1, 1 1 is something here, this is 1 1. Next is 0 2, 0 2 is something here. And what is the convex hull of these 3 points now? The convex hull of these 3 points is this triangle. Okay. So, now are they disjoint? Because this convex hull, this triangle of A plus and this convex hull of A minus, they are not disjoint because this is common. So, since they are not disjoint, so they are not linearly separable. So, not linearly separable. You can also see by geometry. See, we are having these 3 points here and we are having these 3 points here. So, you cannot find a plane such that we can classify these two data points, these two classes. So, this is the first most result, that if the convex hull of two classes are disjoint, then they are linearly separable and vice versa. But again, this it is a very small set. So, we can say, we can find the convex hull and we can say that they are disjoint or not. But how we can say that whether a given sets, mathematically how can we show that whether a given two data points are linearly separable or not. So, we have one result based on error minimizing LPP, which will deal with that by formulating that problem into LPP, we can see that whether a given problem, whether a given binary classification problem is linearly separable or not. But before going into that result, first we will see, first we have to understand this inequality, this result. What this result is basically, that the inequality A plus W greater than EB and A minus W less than EB by suitable scaling can be rewritten as this. Why and how? Is it true? Is it really true? So, that we have to see. Okay. Because why we are doing like this? See, if we are having a strictly greater than or strictly less than type of constraints and we are formulating a LPP, it is not easy to solve such problems. See, if we are having less than equal to or greater than equal to type constraint or equality type constraint in LPP, that we have different methods, different algorithms to solve such problems, but not of strictly greater or strictly less. So, we anyhow we want to convert these strict inequality type constraint into less than equal to or greater than equal to type constraint. So, how can we convert these two constraints to these types? So, let us try to understand. So, the first constraint is a plus w greater than E b. From where we get this constraint? Because if you are having two class of data points, one denoted by a cross, other denoted by a dot suppose, and you are having a hyperplane which is w transpose x equal to b, which can classify these two classes linearly, then for one class of data points this inequality will hold, and for other class of data point another inequality will hold. Okay. Now, how can we convert this and this inequality a minus w less than E b? Okay. One is greater, one is less. Now, let us try to understand. Now, so this a plus w which is greater than E b implies a plus w is greater than equal to E b minus say alpha I, where alpha i's are greater than 0 for all I. It is greater, greater means plus, because if it is greater than E b, then it is further greater than E b plus alpha I, because alpha I is strictly greater than 0, of course, because E b is greater than E b plus alpha I. Okay. Now, let us take alpha star is equal to minimum of alpha I, minimum over I. It is minimum of alpha I, it is minimum alpha I, suppose alpha star. So, that implies alpha star is less than equals to alpha I for all I. Okay. So, that means a plus w will be greater than equals to E b, which is alpha I, that will be again greater than equal to E b plus alpha star times E, because alpha I is greater than equal to alpha star for all I. So, this implies a plus w is greater than equals to b plus alpha star times E. So, this is suppose 1. Now, let us take a minus w less than E b. So, this further implies a minus w is less than or equal to E b minus say beta I, where beta I is greater than 0 for all I, again beta j you can take beta j, okay, because E b will be less than or equal to E b minus beta j. So, this further implies a minus w will be less than equals to E b plus beta star times E, where beta star is equal to minimum of beta j. Because here from here, so in the same way as we did here, will be less than equals to beta j. So, it is minus. So, here it is minus, sorry. So, negative of beta star will be greater than or equal to minus of beta j. So, that means this will be minus of beta j. So, that means minus of beta j will be less than equal to beta star. So, this is second expression suppose. So, now if you choose, now let gamma equal to minimum of alpha star beta star. So, this implies gamma will be less than equals to alpha star, and gamma is again less than equal to beta star. So, what does 1 implies then? 1 implies, see, alpha star from here alpha star is greater than equals to gamma. Okay. So from here, from this inequality 1, what we have concluded? So, this will be A plus W greater than equals to B E plus gamma E. Okay. And from 2, what we obtain? A minus W will be less than equals to B E minus gamma E. This you can understand from here, because minus beta star will be further less than or equal to gamma from here. Okay. So, now these two inequalities can be further written as this, the above inequalities can be rewritten as, now you can divide by gamma throughout, and again you are here also you can divide by gamma throughout. So, you will obtain A plus say W star greater than equals to B star times E plus E, and A minus say W star is less than equals to B star times E minus E. Okay. Where W star is nothing but W upon gamma, and B star is nothing but B upon gamma. So, in this way we have converted the strict type of inequalities into less than equal to or greater than equal to types. So, that is basically suitable scaling. So, suitable scaling will not affect, see we have only changed W or B by applying some constant gamma. Okay. If they are linearly separable, still they will be linearly separable, and if they are non-linearly separable, then still they will be non-linearly separable. So, we have seen that if we have two classes of, we are labeling with +1 or -1, and we try to see that whether they are linearly separable or not. The first way out is, if we are able to find a plane which then classify them linearly, that means they are linearly separable. Next is, if you find the convex hulls of the two classes and they are coming out to be disjoint, then we can say that they are linearly separable. So, these are references which we have used here. So, thank you.